một. Ok, ở đây chúng ta bắt đầu.
Không cảm nha. Cái này nói tiếng Việt không có được, nói thiệt luôn. Okay, so, okay, so just to remind everyone, just to make sure that we haven't forgotten everything because of water and the fruit and everything. So what is rendering? So rendering is to take a scene description, which is basically in this case the geometry, the texture, and the lighting, and create an image out of it. So that is rendering. That's computer graphics in a sense. That's what I told you in the previous lecture. And inverse rendering, as the name suggested, is how to go backwards from an image and try to recreate the geometry, the lighting, and things like that. So inverse rendering can be considered to be like a subfield computer vision. So there's a school of thought of computer vision, which is computer vision as inverse rendering. So here I would consider it to be computer vision. It's not everything, but for the sake of argument here, let's just say it's computer vision. So rendering, in computer graphics, rendering took its peak in 1999. And since then, we have managed to render really high quality images, things that you see in films and games and things like that, out from geometry. So this is a very, very mature field in computer graphics. So we're talking about not only like high budget movies and things like that, but we're talking about architecture visualization, which is very popular and very well commercialized. We're talking about Interstellar, my favorite movie, like awesome rendering, I have to say. We're talking about very realistic human face rendering. Actually, I just saw on Twitter today that there's a advertisement agency in Japan where they now start to use digital model to create their advertisement. So they won't have to take photos of models anymore, they just create whatever they want on digital models. And it's so realistic that people couldn't recognize whether it's digital or not. But the problem with the computer graphics pipeline of rendering is that it's super slow. You're talking about a lot of resources and very long time of rendering. So that is kind of like a barrier to entry to lots of people, especially now we have a lot of game developers or like independent movie makers who also want to use technology, and they just cannot afford to pay for the rendering farm to produce all of these images. But from a computer vision perspective, the biggest problem with this pipeline is the indifferentiability of this rendering equation. So remember this image when I just showed in the previous lecture, where to render a pixel on the image, you have to consider lighting and things like that, and you also have to consider visibility, whether this object is being seen in the scene or not. And because it's a step function, you really cannot do gradient descent through it. So although in computer graphics you have super highly realistic images rendering pipeline, they cannot be used for computer vision application right now. They just used to create very good movies, and that's it. So that's computer graphics. In computer vision, again, state of the art of GAN, you can now generate really highly realistic images as well in very high resolution. You're talking about 1024 by 1024 images. Very realistic, so that's great. The problem with this GAN model is that because right now it's a probabilistic model, so you can only sample the images out of them. You cannot control what kind of images that you have. For example, if I ask a GAN model, so for example, take the model on top, it was trained on face images, right? It can generate really nice looking face images, really handsome actors and things like that. But now if I ask the model, hey, can you give me an image of an Asian female with glasses and lipstick. There's no way that this model can do that information right now. In theory, if you have the labels for those properties, you can train a model for that, but in case if you don't have any labels, like, there's no way you can do it. So that's the problem right now. Another problem is that although this model can generate really good looking images, they're actually not that smart. In what sense? Let's think about it. So if you want to do classification, I keep coming back to classification. You can, in theory, you can do classification on the 2D domain. In the sense that I can give you a picture of objects, and only by looking at those images, you can tell which object it is. That's great. But for tasks like, let's say, for tasks like robotic vision, for example, where you really need to understand the 3D world, you really need to understand depth information, because otherwise the robot will keep hitting to a table or something. Then these models right now is very bad at them. It basically has no understanding of the 3D world. So a very simple test, for example. So first I ask the model, hey, can you generate a bunch of chairs images for me? Okay, perfect, easy, piece of cake. Now, can you generate the same chair, but from a different pose? That is when the model starts to fail, because in order to do rotation, especially what we call out-of-plane rotation, this model really struggles, because you really need to understand the 3D world to do this task. And this is where you see they start to have very noticeable artifacts, or become very blurry, because the model just don't know what to do, because it doesn't understand the 3D world. So that's the problem with models. If you look at how these models are being designed, it kind of makes sense why these models don't understand the 3D world at all. All of these models are built on CNNs, right? Convolution neural network. If you come back to what is a convolution, let's ignore the nonlinearity, let's ignore the pooling, just look at the convolution. It's literally just a 2D operation, right? It's a linear 2D operation. There's no information about 3D world in here. It literally just take a pixel, multiply some numbers, that's it. And somehow it detects some edge, but it can detect edges and things like that, but it really doesn't know how these edges are fitted into a 3D world. It doesn't know that, because it's a purely 2D operation. So again, all of this model, DC-GAN or Nullable, they all use 2D convolutions to generate images. So my interest, or basically what I'm trying to propose in my PhD thesis, is that what if we add the knowledge about the 3D world in this model in order to help us understand the 3D world better. So the technical term is inductive biases. So inductive biases is the formal definition is that things that help the model learn without any, even without seeing any data. It's kind of like a built-in intuition. It's kind of like a built-in inert knowledge before we even start learning anything. That's the inductive bias. So I'm interested in adding this knowledge, this pre-known knowledge about the 3D world to these models to help them understand the 3D world better. And this is highly inspired by the computer graphics literature, and I'm going to say in details later how.